Hello, Narnach here. Welcome back to ShenZhen I. This is gonna be the episode for the pulse generator, the very first real puzzle in this puzzle programming game. So let's start out with a little bit of lore fluff. Why are we doing this? In order to test some of our new manufacturing equipment, we need a pulse generator with certain requirements, specifications. However, instead of buying one at the market price, I thought we could simply create our own. For this project, you will need to make use of conditional execution. Please continue your study of the language reference. So this is yet another gentle reminder that you should not throw the game's manual into the corner of your room. You really should keep it at hand, because the game's manual with especially the bit on the language reference is really useful, and they point out that conditional execution is going to be useful here. So let's have a look at it. I've got 4 different solutions that I want to show you. Let's start with the very first one. My background is I played a lot of TS 100, where you didn't have really highly advanced instructions and you didn't have a lot of memory to work with. So sometimes you ended up doing interesting things and you kept a lot of program state basically by jumping from label to label, and depending on where you are in the execution in the program, defined the state where you were, rather than storing it actually as a data. This is the most complicated solution and also the least efficient one, but that's why I started out with it. So if you do this, you might end up with something like this, and that is okay. So we have a simple input here, which a button is connected to. We have a simple output, which a pulse generator is connected to. And when someone pushes the button, which in this game, anytime a button is pushed or a signal is on, a value of 100 is transmitted. If it's not, it's going to be a 0 value. So 0, 100, it's on and off. So if the button is on, we keep generating a pulse. Turn on the pulse, we turn it off, turn it on off, on, off. And we keep repeating it as long as the button is pressed. Once we stop pressing the button, we stop generating the pulse. So how do we do that in our very first solution? Button goes to P0, the pulse goes to P1. So what we do here is we start in an off state. We check, is the input here equal to 100? Basically, is the button on? If that is the case, we use a new feature of this game, conditional execution. You see the plus before here, which indicates if the previous conditional check was positive, this line activates and we jump to the label on. If it's not the case, then this one is grayed out, and I'll actually show you before we go back. So by default, all the things with a plus or a minus are grayed out because no conditional execution has happened yet, and therefore the game doesn't know whether it should or should not allow execution of these things. You first do the test, and then you can act on it. So we test, is the input value equal to 100? Well, that isn't the case, because it defaults to 0, and here it is 0. So we skip this one. It stays grayed out. It doesn't consume any power. It just doesn't exist for now. Then we go to the next one. We move a value of 0 to the output, to P1. So what we do is we tell the pulse to be off. That's just the very same default. And after that, we sleep for 1 second, for 1 time interval. And then after that, we jump back to the off label. So nothing really happened. There's no input, so we tell the pulse generator to be off, and that is it. We check, nothing. So we do that a couple more times, and then we go to where the button is pressed. So let's have a look. We check, is the input equal to 100? And now we see it is. So we step further, and now you see that the conditional execution here is not grayed out, it's actually active. So once we step into it, this one gets executed and we move on to the next label, on, where we move a value of 100 to P1. We are turning the pulse signal on. So we step into that, value of 100 goes in, and then we sleep, and therefore this one ends with a value of 100. Okay, next time interval. we step on. You might notice the grayed out one here. We test if the input is still equal to 100, which is the case. The button is still pressed. So there's no reason to execute to jump. We are currently just continuing our execution of our hey, we are pulsing state. So we just send out a value of 1. So next up we need to send out a value of 0, because otherwise it's just going to be a continuous signal. So we send out a move a 0 to P1, and you notice that it turns off. And then we sleep again for 1 second to allow the time to advance. And then basically we want to repeat the same thing. So what we do here is we test if the input is still equal to 0 or to 100. Basically, is it still pressed? If that's not the case, we jump out. If it is so, we jump back to on. We go back to where we started. And I realize just a interesting little thingamajig. We could also just drop the final 3 lines here in order to move it, because this test equal P0 to 100 is the same as the very first line, and it's also the same state. So we are literally doing the same thing. So what we can do here is we can stop and we can say, well, we just select these lines. If you can hold shift, you can do selections, hit delete, remove it, and then we'll see. Oh, we're just pulsing through. So a little bit of a micro optimization for arguably one of the least efficient solutions I already had, but it just became a little bit more efficient. That's one of the reasons why I like games like this. There's always room for improvement. Even if you're just showing the very first simple solutions, there's always room for more improvement. So if we just simulate this, it's gonna score better than before, which is nice. And you see there's multiple variations of patterns of input. So if you're trying to exactly fit your output to the solution or to the inputs, the sheer amount of different inputs that you get will eventually force you to actually implement the proper solution rather than the easy solution. So we improved our score, but we still haven't managed to beat our best. So we continue editing, we jump out of this. Okay, so we've used a 5 yen component, but in the score overview here we see we can also do it for 3. So let's see if we can squeeze everything into a $3 component, which is smaller and therefore it has less lines, and therefore the more complex solution that we previously had didn't fit. Though maybe with chopping off those last 3 lines might have actually allowed us to cram it in. But this is a different solution, so it's always interesting to show you the how and why. So here we are using the accumulator, the AC memory register, to store a state. So what we do here, once again, we just step into it. A lot of things, we use a lot of conditional execution here, which, well, we embrace what our email instructions told us to. We test if the input is equal to 100 to see if the signal is on. Well, in this case, it's not the case, so we step over. So this one activates. So we move a value of 0 into the accumulator. Okay. For now, we don't know the context. It will become apparent later on. Then, again, we do the same thing. And then we move the accumulator value back out. Okay, so we send it out and then we sleep. So, button is off, pulse generator is off. There is some symmetry there. And this repeats a couple times because the input is just gonna stay at 0 and this is not gonna change. So, now we get to the cycle where the power is turned on. So, let's have a look. If the power is on, then suddenly all the conditionals flip. So, we test if the accumulator is equal to 0. Then we continue with the next line, which is the case. And then we move a value of 100 into the accumulator. So on a successive run through, because this value is different, this test is gonna get a different result, and we will use the other instruction over here, which puts a 0 in it. So This allows us to flip the value of the accumulator from 100 to 1 and back and forth. There is actually an instruction for that as well, but we're not using it here for now because we're just keeping it very, very simple. And I didn't think of that at the time. So, and then here, because the value is 100 now, we send it out. And then we sleep, because of course we always want to sleep and wait for the input to refresh. But luckily, the button is still pressed, so we're pulsing. So we're gonna check once more. Is the value equal to 0? Well, it's 100, so it's not equal to 0. So things are gonna change again. And then we move a value of 0 through to the accumulator. So we reset the value here. And then we send it out. And then we sleep for a second and we go back. So now we are pulsing through, and as long as this one is on, the value is just gonna turn on and off, on and off, on and off. And then once this one turns off, the value is at 0 now. Then we move the value of 0 into the accumulator and we turn it off no matter whether it was on or off previously. And I realize we can actually take this instruction out and it should still work. Exactly. Because we were moving, if the input is not 100, so if it's 0, we were moving 0 into the accumulator and then again moving 0 into the accumulator. And that would never change. So by taking out the first one, we always made it work. So if we hit the simulator, it's just gonna advance and it's gonna get better. So once again, slightly better power usage, and we did manage to do it with a small 3N component. So here you see a noticeable improvement in the score, but this is not it. So I was thinking, what if you have one component? Then you're doing a lot of things, because on the one hand you have the button is pushed and you're trying to determine, is the button pushed and is it still pushed? On the other hand, you are generating a pulse, which is its very own thing. So what if we add two components that both have their own function? A bit more overhead, you got some communication between the components, but there's ample space, so this might be one of the better solutions. So the left one, it checks for the input. If it's equal to 100, then it's on. Then we send out a value of 100 to X1, which uses the X-bus system, which has this nice yellow dot next to it, which is, it's like a message bus. Rather than having a continuous signal, it puts in a value and the other end can read out the value. And if the other end is reading a value, but there's nothing written into it, it's gonna block and wait until you actually get a value. So you can use it for efficient communication between components if you only wanna transmit a value once. So one of the insights that I'm using here is if a button is pressed, then you're always gonna pulse it on and it's gonna pulse off. That always happens, it's gonna be on and off. So you never really need to double check whether the button is still pressed here or not, because it's gonna be off no matter what. And here you can see that as well. Here the signal is on during the on and off phase of the button pulse, but here we stop pressing the button after our on pulse is done and we still get an off. And you know, if it were to be on here, it would behave like the previous pulse and things would just go on as they were. So you can look at it, if on the first time unit the pulse, the button is on, then you know this sequence is always going to happen, on followed by an off. So that's exactly what we use here. We just check, is the button pressed? If so, we send a signal to the other side and we sleep for 2 whole seconds, because we know we're going to send a pulse on and a pulse off, and after that we can double check. If that's not the case, if this wasn't on, then we only sleep for 1, because well, we never know how much time there is between different pulses. So we need to check every second for a new value. So that's what this one does. On the other side, we use SLX. We sleep until there is input on x0. So that's a conditional sleep, which is nice and easy because this entire component will not do anything until we put a message into x1, which will be read over here, and we can emit a pulse. So what we then do is we check, is it equal to 100? And that's basically just to get the message off of the message bus. That's the only reason we do that. You could also just move it into accumulator or do anything that, as long as you just consume the input. In this case, I chose to make it slightly more robust. We just check if it's 100. If that's the case, then we send out a value of 100 to the pulse. We sleep, and then we send out a 0 again to the pulse, and we sleep waiting for new input. Because we reset it, and then we really don't care how long we sleep, so there's no need to sleep in one extra cycle after it to wait for the cycle to finish. So that's how this one works. And as you see, this message is coming through. So we can actually just step through. So here the button is pushed. We put a value of 100 in. Here we are sleeping until there's a value. Here it picked up the value, so it actually moved forward. The message is still in here because the sleep doesn't consume your value. Then we do a test, which actually pulls the message off of the input, so it gets consumed. Well, it's equal to 100, so we move a value of 100 to the pulse. Then we sleep. Then we move it, the value of 0 back. And in here, we are still in our sleep too, so once we advance time once more, this one goes further, and we still sleep until another value goes through. And we simulate this, and it just works pretty beautifully. But you might notice there's not a lot of code here. So could we maybe do this in a single instruction? Because now telling another component to go on or off, couldn't we just do that with a single instruction and then just have everything afterwards append to it? So that's indeed what I ended up with in here. So we have an input, we have an output, very simple, no XBus inter microprocessor communications. We very simply test if the input is equal to 100, which is not going to be the case in the very first couple of inputs. So if that's not the case, then we just move a value of 0 out and we sleep. And then when things change, when the value actually goes to 100, then our conditional executions kick in. So we move a value of 100 out, and then we sleep for 1. And then we move a value of 0 out, and we sleep for 1. Basically, we execute a pulse, and after that, we go back to checking. And indeed, this just generates the output as expected. And this has been my most efficient solution so far. Now that I'm looking at it, this is an episode of insights while working on things, which is nice. Means there's room for improvement. So the very first time, the components always default to 0. So there's no output. At least simple components, they always default to 0. So there's not a need even to send out our reset signal. Well, actually, we do need to sleep, but there's no need to do the reset signal. So could we move this instruction to the conditional as well? So if there's a value of 100, then what we do is we send out a value of 100, we sleep, and we send out a value of 0. So we start with 0, we change it, and we reset to 0. And that's the only thing we do once we actually get a pulse input. Otherwise, all we do is sleep and wait for the next one. And I think this might actually work. And this, for every cycle through where we are not pressing the button, that saves us 1 instruction. So that saves us 1 power cycle. So this is going to be an even more efficient solution than before. and now it's now 139. I think I had it at 161 before, so this is definitely an improvement. And you see different random patterns, you get different power usages. So 140 for this solution. And that is the best one I've had so far. If you have had an even more efficient solution or a more creative solution, please feel free to leave a comment below. No, it might not be useful for me, but it might be useful for other people that are looking for an even better solution. So, as always, I'm gonna thank you very much for watching. I hope you enjoyed this episode, and I hope to see you again next time when we have a look at the light up signs. Bye bye.